reminder, we are recording this. You should get a notification right now. And as always, if you have any questions, go ahead and put them in the chat and we will answer them at the end. So just as a recap, this series of webinars are building blocks that we will continue to add to throughout the year. We began with the ASHRAE Epidemic Task Force, followed with the physics of pathogen migration last month. And today we are laying another foundation block with ASHRAE 62.1, the standard for ventilation, system design, and acceptable indoor air quality. So today we have a special guest speaker, Hoy Bohannon. Hoy is president of Hoy Bohannon Engineering, a firm that works closely with clients to promote healthy, sustainable environments and improve energy efficiency with a focus on existing mission-critical buildings. Hoy has written technical papers and articles on indoor air quality, operations and maintenance, and is an ASHRAE Distinguished Lecturer. He is past chair of 62.1 and is currently a member of 62.2. He writes and teaches courses for the ASHRAE Learning Institute and is a recipient of the ASHRAE Distinguished Service Award and a PENC Fellow. So needless to say, we are all in for a treat as Hoy discusses ASHRAE 62.1 and the requirements of the standard with emphasis on the most recent changes that are intended to allow designers more flexibility in complying with the standard and providing better IAQ. So Hoy, the floor is all yours.
Thank you, Kelly. Pleased to have this opportunity to speak to this large audience you've put together. And starting out with my slide on Happy St. Patrick's Day. Again, maybe by the next St. Patrick's Day, we can all get together in person and do these things. But at this point, we're on Zoom or something else. So let's get started because I always have more to say than I have time. So we'll get through this. And part of, I think, what we put out there as an idea for the slide or the topic was better design using new options in ASHRAE Standard 62.1 2019. So what I always start with is some background, right? Why are we doing this? So the question is, how does ventilation work? What's the big idea? What do we want to do? So again, when we're all in the room, somebody says, oh, well, we want to bring in outdoor air, right? That's the big idea. We want to bring in outdoor, that's what ventilation is. And then I say, oh, do we really? Does it depend, right? Does it make a difference on where we are as to whether we want to bring in this outdoor air? And of course, obviously from these pictures, it does. You don't want to be in any of these places directly and bring in the outdoor air and think that it's good. And so there are also different places in the world, Beijing, New Delhi, where you just generally don't want to bring in lots of that outdoor air. So let's talk about why we have this idea of outdoor air, where it came from, and what we're doing as ASHRAE, because this is, there's most of us, I would assume, are ASHRAE members, or if not, you know what ASHRAE is. And the initial establishment from ASHRAE was the American Society of Heating and Ventilating Engineers in 1894. Well, that's going back like 127 years now. It's been a while. So what were they talking about in 1894? Why in the world did engineers get together and what were they doing? Because things were very different. I mean, we didn't have cars, we didn't have Fords, we didn't have any of those things. We had horses and buggies and really didn't have electricity for the most part. So what was going on? Well, it was a sign of the time. There were heating systems and ventilation systems. So we think about heating systems. What were those? Those were mostly boilers, right? And so why do you want engineers involved with boilers? Because if boilers are not done right and we don't figure out how to size them and how to operate them correctly, you have an accident with a boiler, you have a big kaboom, right? So how do you make the heating system work as we're building these buildings in that period of time? And the buildings were going up 4 floors, 5 floors, running heating and piping through the building. So you wanted to do that, but there's also ventilation systems. So ventilation systems really dealt with what's going on in these areas. We had factories, we had areas where we had to try and control what's going on. But we also knew that we had, the other driver was we had compulsory school. By 1900, 34 states had compulsory schooling laws. So what did that mean? That meant you had all these kids that were getting together, but that before that, it was really about in the 1870s or 80s that there was this idea that we should have education, right? That it should be, the government should support education, we should have education. And so we had these schools being created, and you put all these kids in the classroom. Well, what happens? They used to be running around in the farm, feeding the chickens and doing all those things, but now they're all put together. And what we found were that there were diseases. Kids would get sick, right? They still do that the same. The diseases are different. You put all the kids in the room, one kid gets the cold, they spread it around to the other kids and bring it home, and there you go. Well, the diseases were different. They were more serious and fatal. And so in the day, it said, well, what do we do here? There were studies, actually epidemiology studies, some of the first ones, where you had all the kids in the classroom, you had other kids that were outside. The kids outside didn't get sick. The kids that were in the enclosed classroom did get sick. So the question is, how do you do that? How much ventilation? And so ASHRAE came up with what the ventilation rate should be. Basically had to do with opening windows, how big would the windows be? So if we look at the history, tuberculosis is one we can pick out. So tuberculosis, if we can look at the graph down in the left-hand corner, in the 1880s and 90s, we knew that it was from a bacillus, from a bacteria, was identified. There was skin testing, so you could tell who had tuberculosis, who didn't, and it started to just kind of drop off because there was a recognition of how to control TB. And this is the mortality, the death rate, mortality rate per 100,000. So it was going down, but the idea of ventilation then was, hey, we need to ventilate because it affects health. And in fact, it was still so serious during the Second World War that we've got this poster from Kentucky that said there were more people killed from tuberculosis during the Second World War than there were killed in battle or died of wounds or disease in the Second World War of the soldiers from Kentucky. So it was still a big issue, and it really didn't get under control until there were antibiotics that affected TB. And so by the 1950s, it was pretty much not a big deal, right, in terms of tuberculosis, but there still were some other airborne diseases. So if we look at the ventilation rates in CFM per person, the American Society of Heating and Ventilation Engineers came up with a number in consulting with the medical community of 30 CFM per person. And then there was a question of, is indoor air quality a function of temperature or volume or humidity, or do all these things affect it? And the answer, by the 1930s, there was research at Yale that said, nah, that's not really that. We've just got this thing that it really has to do with ventilation and the rates per person. And so Professor Yaglu at Yale came up with rates that were something between 12 and 20 CFM per person for adults and 17 to 25 for children. In 1973, ASHRAE published the first ventilation standard. ASHRAE really didn't have a standard. There were articles, there were things that were in the engineer's designer handbooks, but ASHRAE didn't really establish standard until 73. And it said 15 CFM minimum, 20s recommended. Well, we don't do that anymore, because if we say minimum and recommended, then we get all kinds of controversy about why aren't you doing what's recommended and so forth. So at this point, we're not doing that. We had then the next change, the major change in ASHRAE 62 was in 1981. And that change came about because of something that happened in society, and that was the energy crisis. So in the 70s, we were using lots of energy, lots of it was being imported. And when the Saudis shut off the pipeline that went to the ships that brought the oil over to us, we had an energy crisis because we couldn't drive our cars, right? So I glanced quickly at the sign-up sheet, and we've got people in Arizona and New Mexico and Texas and Kansas, and out in those areas. We're not in New York City. I'm not in New York City. I'm in kind of a smaller town in North Carolina. we have to drive our cars. We like driving our cars. So what happens when you can't drive your car? Everybody gets upset and you complain to Congress and you say, we're going to do something about it. Well, ASHRAE did something. They came up with ASHRAE Standard 90.1, the energy standard for buildings. Didn't exist before the energy crisis. What else did they do? They said, well, there's other things we know with it. You know, tuberculosis has gone away. We don't really need all this air in buildings. It costs a lot to ventilate this air and heat and cool this air we bring into our buildings. So in 1981, ASHRAE changed the standard to 5 CFM per person. In North Carolina, where I live, these standards go into the codes. The building code in North Carolina from the 70s or from the 80s said you shall have no more than 5 CFM per person in your design, which meant that they encouraged and people went around and boarded up all the outdoor air intakes because it was going to save us energy. And we sealed all the cracks and we put all these people in the buildings and everybody's in the building, but we're bringing in all this new modern furniture and all this other stuff. And so there's a thing called the law of unintended consequences. Nobody intended this, but we found out the hard way that there's things we didn't know about. Who knew that a building could be sick? Nobody knew that before we shut off the ventilation, and we had a sick building. We had building related illnesses. So what happened to that? Well, ASHRAE said, oh, gee, there were lots of conferences on indoor air quality. There were lots of conferences in papers at ASHRAE, lots of discussion. And there was research in the 1980s that said, yeah, we really need this 15 CFM of outdoor air for occupant odors and acceptability. And it also then looked at what happens with health. And so that was all a consideration. And the committee that wrote ASHRAE 62 came up and said in 1969, gee, we don't really like what happened in 1981. Let's just put it back the way it was. Okay, put it back the way it was. So we went back to 15 to 20 CFM per person in the 1989 version of the standard. Now that wasn't totally popular with everybody. The energy guys said, well, you've overreacted. We could still save energy. Maybe 5 was the wrong number, but we could really cut down on energy and come up with ways to save energy. And I'm certainly an advocate for saving energy, but I'm also an advocate for not going back to this, right? We don't want to go back here. We already know that doesn't work. So what do? So we put it back the way it was, and now we've got a consciousness about, gee, there could actually be an airborne disease that we're concerned about. Ah, well, who would have thought that? Well, nobody. Some people did. Some people said, oh, there's going to be a pandemic someday. It's going to happen. We're going to have this disease come out. So we now know that there is an airborne disease. We're all concerned about it. We're all not in the same room because of it. It's spread by people and it's spread through the air. And it's spread through something called droplet nuclei or aerosols, which are even smaller. So again, I don't know who this guy is in this picture. It's in the public domain. Everybody uses this picture. He's famous. He's in every presentation and every article, but it's a very clear picture of what happens when he sneezes, right? You've got these big droplets, which are the droplet nuclei, and then you've got this kind of cloudy, fuzzy stuff, which are the aerosols that float out into the air. And so what do we do about that? We do have now a connection between what's in the air and our health. I just threw these in because I thought it was interesting. I presented this same presentation back in must have been the 17th of February, 2020. And that's when we were still traveling, right? It was before everything totally got shut down, because we look at the United States of America and we had maybe 100 cases of COVID. The focus was all on China. I mean, they had more than 5,000. So it was a big problem. So what happened after that? So what a difference a year makes. So we're looking all over the world and there's a few thousand, right? Cases, 10, 20, adding that up. I don't know. It didn't actually show the number here in this slide, but this was just to say, hey, we've got something to think about. And what was interesting is that 454 cases were on a cruise ship stuck off the coast of Japan, right? So cruise ships, definitely, it was contagious. It moved around. Nobody was really sure about how it happened. We're pretty sure now that it's all has to do with what's in the air. Where are we now? We're at 119 million, 120 million confirmed cases as of the 16th of March. That's yesterday, right? That's where we are. And what's the map look like? Well, you got this little dot sitting there on China, and then because it's by country or by island, you got all these just blobs. It's everywhere. It's a lot, and it's something that's airborne, and we're not really over it. So the question is, do we, does ASHRAE 62, did this ventilation standard deal with that, right? The answer is no, it didn't, because who knew? Who knew? It had been really, since the United States has had a full pandemic, which was basically in 1918, it had been 100 years. We hadn't had that. So who was going to worry about something that happened 100 years ago? We've got vaccines, we've got antibiotics, we don't need to worry about it. So going back in history then, in 2004, between 1989 and 2004, a committee went to put together a new standard 62, and that's what we have now, which says that so it was kind of a win-win. They had health authorities and energy engineers that said, how do we come up with some balance between ventilation and energy? And it basically said there's two sources. We have buildings and we have people, right? And so we can figure out the ventilation rate for people, and we can figure out the ventilation rate for buildings, and we need to add those together. So really, since in this century, that idea of we add things together, it's not just a CFM per person that we did in the last century. We've got these two parts, people and buildings, and we've got the numbers that go into standard 62. So standard 62 purpose is to specify minimum. I'm going to say minimum now, because that's part of, we did this survey, right? I'm going to talk about the survey, but this is the minimum ventilation rates and other measures intended to provide indoor air quality is acceptable to human occupants and minimizes adverse health effects. And that's in normal times. If these are not normal times, so it doesn't really apply to where we are today in terms of COVID. It's intended for regulatory application to new buildings. So it's really code intended. This is a code intended standard ASHRAE is written to try and put into the building code and to guide the IQ for existing building. I've got more things to talk about than what's the scope. It's basically lots and lots of buildings and spaces that we're in, except for residences and hospitals. So there's a survey that was sent out to you in the audience. And so here's a couple of things. Complying with requirements of ASHRAE represents the best engineering practices, and 93% thought that was true. All right, so I hate to burst your bubble, but if we go back here and we say, this is what goes into the code, what's the code? The code is the minimum. So I'm going to tell a real quick story. I bought the house that I'm in about 6 years ago. And I had a home inspector because I was finally old enough as an engineer to know that I didn't know anything. I needed to hire an inspector that knew all the tricks of residential construction that could figure out what was going on in this house. So he went around, we went around and looked at it. And the guy who built the house, the superintendent came up and said, I'll have you know that your house was built to code. Well, he didn't know who he was talking to. I said, okay. So you have just told me you built the worst possible house you could build, because the code is the worst you can do, right? The least you can do. Tell me something you did good. He was dumbfounded and walked away and didn't want to talk to me anymore. The code is the least you can do. So it's not really the best practice. It's the least you can do. So if we want to do best practice, we have to figure out how to go beyond the minimum, beyond the code, and we can pick some things out of ASHRAE 62 that can help us do things better, that are options, right? But the minimum is the code. If the CO2 concentration is less than 1,000, the IQ is good. Look, I've dealt with indoor air quality for more than 30 years. I don't know the answer to that. It's generally, it's not just CO2. If you go to, you can go almost any place in the morning and measure CO2 less than 1,000, and it may be horrible. You know, it doesn't tell you whether there's bacteria in the air. It doesn't tell you whether there's mold. It doesn't tell you whether there's harmful chemicals. It doesn't even tell you if there's carbon monoxide. It doesn't tell you anything other than it's some rough indicator of how many people have been in the building for how long. So it's not really a good metric in terms of whether the IEQ is good or bad, because there's so many different things that are in the indoor air. If a system's set for 15 to 20 CFM per person, then it complies with ASHRAE 62. That was true back in the last century, but in this century, that's just not the right number. You've got to calculate it, and it's in the ballpark, but it may or may not be correct depending on the application. So it's kind of one of these rules of thumb. That's a rule of thumb, and it applies generally sometimes, but not always. Resetting the outdoor air for demand control in multiple systems by return air CO2. If it's multiple zones and you've got a conference room and a bunch of offices and an open area and some other things, you really need to know what's going on in each room and each zone. And so just having one CO2 and a return air in a multiple zone, again, is just like going and getting a grab sample of CO2. It doesn't tell you anything. And it certainly doesn't comply with it doesn't show that you're complying with the requirements of 62.1. So you got to do a little more work than that to figure out what to do in terms of providing the minimum air, but also trying to save some energy. So again, we've got these outdoor air requirements. Basically, from the people I've looked at that were signed up in the locations, you're all in pretty good outdoor air areas. So you don't have to worry about it. If you're up in the LA area, it's pretty bad outdoor air. If you're nobody's in New Delhi or Beijing, which is really bad outdoor air. So we're going to say generally our outdoor air is pretty good, but we may have some air cleaning requirements. Generally, we want, and 62 does require, that we have filters above any cooling coils or wetted surfaces. Almost everybody that I've seen in these climates, except it showed a couple of people from Quebec that may be on the line. Everybody else, we've got air conditioning, right? You've got a cooling coil, it's going to be wet. You've got to have at least a MERV to keep mold from growing on your coil. That's a required. One change in 62 I want to alert you to is that there was this for 15 years, this idea that we wanted to have this percentage humidity control. Lou Harriman, who literally wrote the book on humidity for ASHRAE, came up to me when I was chair, or actually before I was chair, and said, "Hey, you guys need to fix things in 62. I said, "Well, Lou, you got to tell us what we need to do. We don't know. If you know how to make it better, tell us." And so he did, and came in and said, "Look, what we really need to do is worry about dewpoint, because thinking about it rationally as engineers, dewpoint is the amount of moisture that's in the air. Relative humidity is relative to the temperature. It's not how much moisture is in the air. It's relative to how much the air can absorb. So the dewpoint is really more critical. So right now, the requirement in 62 says we got to have systems that keep the dewpoint below 60 Fahrenheit. The example is you've got a 54 dew point when the systems are operating. It goes up whenever systems are turned off, and you've got all this mold. And this is actually in a hospital. This is bad. This is Lou's example, courtesy of Lou. So dew point's really more important than relative humidity. You can change the relative humidity by cranking the temperature up. But the dew point is really what the driver would be. So let's get down to the ventilation. This is what your challenge in design is going to be, and what we want to talk about how to do better design, and that is the requirements in the procedures. There's 3 procedures in 62.1. They've been there, goodness, back since 1981. There's been the ventilation rate procedure, the IAQ procedure, and the natural ventilation procedure. The ventilation rate procedures changed. That's what most everybody uses, and that's what I'm going to talk about. I've got one slide on the IAQ procedure that's going to give you a warning. If you think you want to use that, make sure you know what you're doing. If you claim you want to comply with ASHRAE 62, and 2 or 3 slides on natural ventilation. which I think is greatly improved from what it was before. You may want to have some hybrid systems in the climates you're in, where the weather's moderate in the winter and you can bring in lots of air through natural ventilation, and then in the summer, figure out how to go back to your air conditioning systems. So again, the ventilation rate procedure, since 2004, and this was put out to public review in sometime like 2001. So really for this century, we've had this idea that's been accepted, and nobody's talking about changing this, that we have a rate per person and a rate per area, and those combined give you the amount of air you need in the breathing zone for ventilation. So the breathing zone is what? It's where we are right now. We're all sitting in chairs, we're in the breathing zone, right? We're laying on the floor, we're pretty close to the breathing zone. If we're standing up in the breathing zone, we're still in the breathing zone. If you climb up on a ladder, you're not in the breathing zone anymore. All right, so it's basically where we're going to typically breathe within a room between 6 inches and 6 feet off the floor is the breathing zone. So the amount of air that we've got to bring in to the breathing zone through each outlet in the room, how much you bring in to each zone. The ventilation per zone is the ventilation of the breathing zone divided by this factor that's called E sub Z, which is the zone air distribution effectiveness. So we've got part of the table. This was the table. It was 6.2.2.2. It says this is a simple one. So usually I'm talking about just the simple one. All right. The simple one is, oh, gee, if we've got a zone air distribution effectiveness of 1, if we've got temperate air or cold air, what's cold air do? What do we know from physics? What do we know from science? Cold air is going to fall. So almost it doesn't depend, it doesn't matter how you distribute the air. The cold air is going to go down. And then if you've got exhaust at the ceiling or the return at the ceiling, it's going to get back out. And there you go. It's going to work, right? What happens is if you don't do it, if you go and you heat the air up and the air is too hot, then what happens is you've got some bypass. And so all the air doesn't get down there. And now you've got to increase the amount of air during heating because it doesn't actually get into the breathing zone. So that's the zone air distribution effectiveness idea, is that the hot air doesn't fall, it actually rises and stays up and you get some bypass. And so now you need 25% more air when you're already heating it up. Oh goodness, so that might be an energy penalty, right? So how do you fix that? I'm not going to talk about how to do that. You guys can figure that out, right? There's other ways to put heat in the building besides this method, which also often, because of cost, is electric resistance heat, right? The least efficient heat we can put in is now not doing what we want to do in terms of how it moves the air around. So there's all kinds of ways of decoupling heating, decoupling air conditioning from ventilation, lots of different design techniques. I'm going to focus more now on what do we do with this E sub Z and what are all the opportunities that we have. So again, the real world is more complicated. The real world is more complicated. It doesn't exactly work like that. And as we start to think about how do we want to design our systems, what do we want to do that might be better for any future pandemic that comes along, or any, what do we do if we want to really separate our breathing zone or what we're breathing from other problems. So the other problems in the past, when 62.1 was put together between basically 1992, it took like 10 years, in 2002, before it changed to 2004, was the idea was, well, we got all this stuff coming out of the buildings, there's formaldehyde and all this, and we've got people and they have bioeffluents and they might have colds and they might have these things. And so we need to figure that out. And that was kind of what the thinking was during that period where the fundamental equation we're using was put together. So it was about ventilation. It was about air's going to mix. It was about, we've got all this data on sick buildings and offices. And so we used all that. So, but now I think it's more complicated. So I've always been in my mind had this idea that if we look at industry, any of you guys that have industrial practices, worked with industrial hygienists, we've got a hospital, we've got laboratories, we take a lot of effort to try and control contaminants, right? We want to get the contaminants away from the breathing zone of the people in the hospital and the breathing zone of the people working in a research lab. So here's a reference for an article Kishore Kankari wrote in the ASHRAE Journal in June 2016. He did this CFD evaluation of a hospital room. He said, okay, here's these different ways we can move the air around the hospital. And here's a base case, the way people usually do it. And if we look at the contaminant that this is coming from the patient that's infected, what does it do? It kind of wanders around the room and goes everywhere. All right, well, here's a different way of laying out the HVAC. And again, the red lines kind of go all the way around the room. And if you do this, well, now we got more dotted lines, but still a lot of red lines. But if we get to case 3 and we actually design to remove what's exhaled by the patient, we could actually make the air go away and not go all over the room. So our mindset as engineers for 50 years has been, we need to mix up all the air because then everybody's going to have the same temperature and we're not going to have hot and cold complaints, because as engineers, we get called back because it's too hot or too cold, or, you know, and then you say, oh, well, this person's too close to the window and we need to put some blinds in and that kind of stuff. It's not too hot and too cold. If we think about ventilation, ventilation's about the health. So ventilation can be, not only do we put air into the building, but how do we take the air out of the building or out of the room? What do we do for better design to protect the visitor or even the people that are in the room, right? The nurses and the staff that are coming into the room. How do we do that? Okay, because Kishore's thrown out one potential. Now, if you do that, do you actually need more air? Maybe not. Maybe if you're very clever in how you make the air move around, as long as you get heating and cooling, let's be efficient in how we use our air. We might not need as much. That's part of the design and the challenge for you to look in the future. So my friend Tom Smith, who does lots of laboratory work, was instrumental, was the chair of that wrote the ANSI Z95 standard, and even the ASHRAE 110 standard was on that committee. Which is a laboratory hood testing standard. Tom is like a global expert on hoods. Said, okay, what's going on here? We're going to do some testing of, and he calls it VEF, ventilation effectiveness. We love acronyms in ASHRAE, and as engineers, we abbreviate everything. Ventilation effectiveness test. So we're going to do this lab configuration. So we set up these configurations of measuring what goes on in the lab, and did some real time. What happens if I generate something over here in the picture? And then that goes throughout the room. How does it go throughout the room? Is it all equal? And in a lab, generally we design labs not to mix everything up. And this lab had an okay design. And so then he moved it around, says, what happens if we move this around again, change the position. So he does all these different changes of positions and what's going on with the air. So here's a simple diagram that you know, he's got tons and tons of data, but the simple diagram of what happened in a layout like this in a lab is at 2 air changes. What's going on at the rate of 2 air changes? What's going on is that whatever's in front of this lab worker is basically drawn over towards the exhaust hood and is taken away from her breathing zone. So the ventilation effectiveness is pretty good in terms of the dose that she's going to get from whatever's coming off of there, which is the stuff coming off the generation area that Tom had set up in the test. So these are real tests that he did in a lab. In a real lab. This is not a mock-up lab. This is not CFD. This is based on real measured data. So he says, okay, so here's your dose, because we're all concerned. The real issue for health is dose, right? It's not that did we walk by somebody that might have had a cold. You know, if you're walking by outdoors, you got all kinds of ventilation. There's not much of anything in the air. But if you're in an enclosed room and the air is moving around as the engineer designed it to do, or maybe intentionally or unintentionally designed it to do, what is it doing? Okay, in this case, the 2 air changes is going away. So if we take this same design, which had the capability in this system to crank it up to 8 air changes, what happens? Well, it puts more air in the room. So by virtue of putting more air in the room, the way it was laid out, it now puts the air down. It eventually goes over to the hood, but it increases the concentration in the breathing zone of the lab worker. And so in terms of the dose is higher and the effectiveness is less. And in fact, one could argue that the ventilation effectiveness with 2 air changes is 10 times better than 8 air changes. And you'd think, oh no, it's the other way around. More air is better. Well, no, it's not. And what are you doing with the air? The real thing we have to start thinking about as we go into the next years, trying to get to zero carbon and all those sorts of goals, is how can we be more efficient? We're using the air as a tool to do certain things. And if the air is supposed to be taking contaminants away, we've got to be really, really smart about how we use this air to take it away. These are extreme examples. These probably don't apply exactly in an office, but it's the same idea. If we're going to try and not spread things around uniformly to everybody, but get the things away, and if humans are the source, how do we get it away from one human so it doesn't go to the other human? There's not any simple answers. It's going to take a lot of work, but that's really the challenge. Let's think about not how to mix everything up so everybody's comfortable, which was the challenge in the 1950s. This is not the 1950s. This is the 2020s. What do we do to get rid of things that are problems that we want to get rid of the building? So the test, again, Tom's conclusion was that the VEF is more important than ACH, the ventilation effectiveness. Most rooms are not well mixed. They had this simple tracer gas, made these measurements. So that's the solution. So you want to optimize the ventilation effectiveness to reduce the air and reduce the air changes, which will save some energy. So that's Tom's idea. That's not 62, right? This is, but it's some research that's out there. So now what's in 62 that's different? What's in 62 that's different is this table has now changed dramatically from what it was for the 15 years before 2019. And now we said, oh, we've got these other things that where the E sub Z, instead of dividing, reduces the amount of air. It's not subfractions. It's, oh, what if we have a stratified air distribution? What if we have something that's really like displacement ventilation? What if we have something that's like personalized air ventilation? And so I'm going to talk about what those things are, right? There's some of that's buried in the handbook, but there's some of it that's new ideas. So this whole idea of what do we do with the air and how do we move it around is really an important thing to understand. So let's talk about an air change. So we think about, oh, one air change. That's some rule of thumb, right? Everything needs to have one air change. So let's say we've got this is actually a glass full of Gatorade, right? So I've got this glass of Gatorade and I'm going to put one air change of water into this glass of Gatorade. All right, so here's the glass of Gatorade, which is our room. We're going to put one air change of water into one air change, one water change right into the glass. We've got one full change, and if it took an hour to do this, this would be the result after one air change per hour. Gosh, still pretty much looks like Gatorade, right? Doesn't really look like water. Well, it's the same thing in our buildings and our rooms, right? One air change doesn't really do anything. To get all that out of there, I didn't try it. I probably need 6 or 8 glasses of water to get it pretty clear where you can't tell that it was tinted, right? That the Gatorade's gone. So one air change per hour really doesn't do a lot of taking things away. We need to be more strategic in how we take things away that we want to get rid of. And so that's where the design opportunity comes within what's in 62.1, the 2019 version, right? So here's displacement ventilation. The idea is that we have temperature comes in, the people are heat sources, it goes up, the heat makes the air rise. And so we've got a concentration that says we've got less concentration here because whatever's coming off the people goes up. Here's an illustration from ASHRAE's IAQ guide. And by the way, if you don't have the IAQ guide, this is one of the best things you can get from ASHRAE because it's free, right? You can download the IAQ guide for free and get these kind of pictures and things that show, hey, what do we do with IAQ? And it's got great illustrations. You can talk to building managers and other people about indoor air quality and things that are important. So here's a representation of displacement ventilation. Again, this is an artist's conception. It doesn't exactly work like that, and it's not really that good, but it's pretty good, right? It's better than the other way of just mixing it all up. as I showed in the Gatorade example, right? You mix it all up, it's still lots of Gatorade. So here's an idea of displacement and personal ventilation, underfloor air and personal ventilation then says that you're doing something here that's putting the air into where the person is. Now this works when people are in the same place, right? It doesn't work when you're running around. You can't have personal ventilation on the basketball court, right? So we're not going to look for that to solve the issues of the Final Four or what's going on in March Madness, right? They're going to be running all over the place, and so you can't really have personal ventilation there, but you could have it where you've got a stable work session, a call center, something like that, where people are in the same place. So here's more examples, courtesy of Chandra Sekhar at the National University of Singapore. Chandra's done a lot of research work on this, and so he's got different ways of having personal ventilation. The other thing, there's some advantages of personal ventilation. Not only does you don't need as much air because you're putting the clean air right there at the person. You don't really need to worry so much about what's going on in the other places because they're just going to transit through the other places. They're not going to live in the other places, right? So it's like if you're in a polluted area and you walk indoors from the polluted area and it's cleaner indoors, it's good. You just transit, you stay indoors, right? You don't stay outside when there's a wildfire or something like that, right? Or you're in Delhi or some other place. So the personal ventilation also tended to lower the inhaled air temperature because you can put it right at the person. And it may not be like this with the nozzle and gooseneck that's up there, but it can also improve ventilation by 50% or more than you can do with mixing ventilation. And the human response was better. So part of what we do with indoor air quality is how do people respond to the air? Their response is better. Okay, here's a tool that if properly used is going to get a better response on their perception of the air quality. And it found that the temperature and flow rate were found to be more critical than the ambient temperature. So if you have some cool air on your face, it's kind of like, we know this, anybody that's worked in industrial, that you can put spot coolers in, right? And somebody that's got a place where they've got to work in a hot factory, they've got a spot cooler, they're going to stand under the spot cooler, right? And it's fine, and they can do their work, especially if the controls are there. We can do the same thing. So we can actually let the temperature in the space be higher, which is going to save some energy. And because almost everybody on this is in an area where we need cooling, so that spot cooler is going to make it better, and you don't need to have as much cooling for the rest of the space where you're not spending very much time. So also in terms of cleaned air and secondary infection, there was some study on that said, gee, there's not as much secondary infection, which means it doesn't get all spread around because you're staying in the clean air stream and you're not exposed to what all the other people are emitting in this office or situation, which could also be a classroom. It could be anything where you can figure out how to come up with personalized ventilation. So there is a normative appendix. See, normative appendix means it can be used mandatory. It can substitute for the requirements, and here's the equation. You can come up with your own E sub Z if you can figure out how to do these equations. There's also a section in the normative appendix that gives you the minimum requirements for using a model to model better effectiveness in alternate procedures. So the real issue in terms of health is getting these contaminant concentrations down, and especially if the contaminant's from another person, we don't really know what it is. We can call it human bioeffluent. That's kind of a term that gets thrown around. How to measure it, it's difficult, but you can figure out how to get the air cleaned out, because typically you're not going to have it in the outdoor air, or you're not going to have it in terms of the bioeffluent we're concerned about indoors with COVID. It really is particles. So if you clean the particles out of the air through your system, it doesn't have to be all outdoor. It can be recirculated air that's highly cleaned. And highly clean for the particles we're worried about with COVID can be MERV 13. It doesn't have to be HEPA. It can be MERV 13. It's going to clean a lot, and so that's part of the challenge and opportunities for new design. How do we get the air to move? How do we get the cleaned air so we've got less exposure, less concentration in the breathing zone for the people that are in the room? So is that a new idea? Well, no, because you actually needed air. But this is the 1940s, right? So it's not a new idea. It's almost 100 years old since we had airplanes that could go high enough you needed oxygen, right? So you've got your personal ventilation, you've got your personal air. The personal air for this is really good, really high E sub Z, because it's all right there and you're not exposed to anything else that's going on outside around you. So the idea then for air distribution is, okay, an air change is not an air change because it really doesn't change. It's kind of misleading, right? You saw me change the water. Well, it didn't really change the water. It just kind of mixed some of it and diluted it a little bit. It's dilution ventilation that we usually use. And so sometimes perfect mixing is a reasonable assumption, like pouring the water into the Gatorade. It just gets all mixed up. If we design our systems to make everybody the same temperature and cool, it'll be all mixed up. So some designs should be driven by really exhaust contaminant removal. So this idea of what we do in the laboratory, what we do in the hospital, really should be more focused on contaminant removal than mixing up all the air. Personal ventilation or displacement may be ideal for some other designs and applications. So in multiple zone recirculating systems, then we've got to divide by this E sub V factor. This E sub V is almost never 1. So you've got to have more air coming in at the outdoor air intake when you divide by the ventilation that you need within the various zones. All right. So the point is you've got more calculations. Not going into that. We don't have time. I wanted to focus on the one thing. Those more calculations have to do with this E sub V. There was a table for that. That table is now gone. That table is in 62 2016. It's not in 2019. 2019 says you use this formula to figure out E sub V. But again, it's going to be a less than 1 kind of number, typically something like 0.75. And then you've got a zone minimum primary airflow to make it work in the typical VAV system. So there's the simplified procedure. If you're going to do better design, you need to go back past the simplified procedure to the more complicated procedure. A quick case study, I've got a friend, James, that has a 2,200 square foot office. He's formerly in a house. What ventilation does he need? Does James need in his office? Assuming James is the only one in there. We've got different ways to calculate it within 62. Appendix F says 30 CFM. Appendix L says 22. If we do the VBZ equation, it says 17. Assuming it's just a single zone. If we do personal ventilation, we can knock that down to 15.5, right? So it's not making a huge difference, but as we start to do these little things to make our energy performance better, we need to continue to look at how to make things better. And this is an example that's very heavily weighted for the floor area and not so much for the person area. So we can't really knock that. If you got a lot more people, a lot more density than person per 200 square feet, you're going to get different numbers. One slide on IQ. P, if you're using the IQ procedure, you shall determine these minimum outdoor airflow and use a subjective occupant evaluation. So you got to actually do this and have people come in and judge the acceptability of the air in the space. That's a requirement that's been there for decades, right? Generally ignored, but it's a real requirement. Natural ventilation, just a couple of quick slides on that, as I'm always running out of time. Natural ventilation really changed. Again, I had somebody come up to me in the hall, Peter Simmons, I think, like 5 or 6 years ago and say, hey, what's this thing in natural ventilation? Where'd those numbers come from? I said, Peter, I don't know. They've always been there, because I wasn't there when they put that together in 1981 or whenever that came from. He said, well, you know what that is? I said, no, Peter, I don't know what that is. You know, tell me. He said, oh, that's an old SIBSI rule of thumb. I said, oh, it's a rule of thumb. Yeah, it's a rule of thumb. It's not the way you actually design natural ventilation. I said, well, help us figure it out. Join the committee. I'm going to name you to the committee, and you can be in charge of putting all this together. And so we had a group of people that very good natural ventilation practitioners and academics put together a new pathway, which talks about how we do engineered systems. Before that, it said you can do an engineered system, but didn't say what it was. So now we say, okay, how do you do an engineered system? What are your criteria for engineering a system for natural ventilation? and what are the openings. So one of the big errors was that it just had to do with opening size. If we think about natural ventilation, it's all driven basically by temperature differentials, right? It's cooler out generally, and in Europe where it's perfected, right? It's cooler outside than it is inside. So we've got to have this flow. The warm air goes out the top, the cool air comes in the bottom. And so we got this flow, we've got this area. So what's the temperature differential from the top of the room to the bottom of the room? If you got A1 at the right, well, you got this differential, right? It's higher at the top and lower at the bottom, and you're going to have airflow. If it's all a strip across the bottom, there's really no driving force. It's not going to work. So the first assumption that was in the previous standard, that all areas are the same, is a bad assumption because it ignored what the driver was for making natural ventilation work. So we can go to James's case studies. There's two different tables, same thing, same office, natural ventilation. He's got three windows. What do you need? Well, if you've got a single opening window, which is the way it goes in every house these days, not double hung, you got single opening because it's cheaper, right? It's cheaper. We put in things that are cheaper. Single opening, we got to have two windows in James's office. But because he's in an old house that had double hung, right, which means you can move top and bottom and have this differential, he only needs one window open, right? Hey, so we've now accounted for that in 62 for natural ventilation. So 62.1, anybody can propose a change to the standard. The notice of proposal is in there. If I'm going to summarize, there's a user's manual. The newer version is in process. The 2019 version will be published, I expect, sometime this year. There's code adoption for much of what's in 62. There's short courses and professional development. There's an IAQ design guideline in process, which is going to go beyond the minimum. So it's going to be more of a best practices rather than what's the minimum, but how do we use these things that can comply with 62, use these things to our advantage to both provide acceptable air to the breathing zone for the people in the building, but also save some energy while we're doing it. Again, the current publication is 2019. It's on a 3-year cycle, so the next one will be 2022. So we'll look forward to something coming out next year. I don't know what it is because I'm not on the inside of the committee anymore. I can consultant. I know what's going on generally, but can't speak to that in terms of being forward-looking. So the IAQ procedure, indoor ozone, carryover and cross-contamination of energy wheels and so forth. Air distribution is an issue. So I really hammered air distribution to get today. What do we do? How do we make it work? And with that, I think I have saved some time for questions by blitzing through all these slides.
No, you did great. So we do have a few questions in the chat. The first one, Alan, I am curious why we do not have a minimum dew point and or RH percentage, a min and max, given what we know about the effects of humidity on our health.
Great. The answer is it was proposed, and the committee decided, both the 62.1 committee and the 170 committee that dealt with hospitals, that they didn't want to get into that at this point in time because of engineering problems that might be caused. I totally agree. I'm the one that submitted the change to put in a minimum. The question is, why did it go away? The reason why it went away is that the comfort research that happened back in the 1990s indicated that people were comfortable with a low humidity, so that went away. So because that made it all go away in the charts and the handbooks, but the idea that low humidity, that we've got a 40 to 60% for us, and it's percent, it's not dew point, percent for us is more healthy is correct. So to the extent you can control your environment, like your home or someplace else, keeping it between 40 to 60% will keep everybody healthier. But it's not in the minimum standards because it's probably not the minimum. It's not convinced. The committee was not convinced that's an appropriate minimum, but it might be a best practice.
Okay. And then a comment from Dan. The EPA has come out and stated that displacement ventilation should be studied more closely for an air distribution in schools. And then he had a question, do underfloor air systems with a floor device located in each worker cubicle qualify as a personal supply source?
Okay. Okay, displacement ventilation is a great idea. I think we need to figure that out and work on it in schools. Underfloor, unless it's engineered to be personal ventilation, it's not. So I would say in general, the answer is no, unless somebody has an engineered way to distribute it directly to the breathing zone of the occupant. I would be really concerned if we're trying to do underfloor in schools, because just think about what the kids are going to drop down through those. I dealt with a data center and you were amazed to find what was down in the floor of the data center when you went in to try and deal with wires. All that needs to be thought through. It's great opportunities, and I think it's something that engineers need to think about and work on, and something we need to work out in the future if we're going to really do a good job of keeping people healthy in very energy efficient buildings.
All right, and there's some concern over the increased cost of the air distribution system with this standard, driving the job over the budget.
Well, you can still do a minimum system. You can put in the old standard VAV and all that stuff, but you're going to use more air. So it's more energy. So it's a trade-off. I mean, nothing's free, right?
Right.
So a high energy performing building is generally going to be more costly than a low energy performing building, or in my view, the code minimum building, right? So you can do inefficient systems and comply with the code, and they're going to be cheap, but cheap is not equivalent to better or, for me, acceptable. But everybody's got their own view of what's acceptable, right?
Also, with regard to current ASHRAE guidelines on reopening of schools, they recommend 2 additional air changes per hour. This is above the suggested air change rates for the space. What happens if you have no ventilation in the space currently? I would not agree that 2 air changes are correct to effectively ventilate.
Well, I'd have to go back and look at the numbers because I think of it at CFM per person. So I'm sure somebody on the task force has gone through all those numbers. You've got a high density of students in the school. You've got a requirement for ballpark 15 CFM per person. So there's a lot of CFM you're going to have to run through that classroom. So if you've got no ventilation at all in your classroom, you're substandard by any definition ever, at least in the last 50 years, right? As far as ASHRAE is concerned. So I know that people think they can get by without ventilation, but every time it gets tried, for instance, the big COVID restaurant issue in China was a place that had no ventilation. It just had mini splits, right? No ventilation at all. And gee, everybody that was at the table got COVID in the restaurant. And I'm not shocked because it just moved it around in the area. So it was everybody that was kind of in the zone that was served by that mini split got COVID. Now, interestingly, the servers didn't because they didn't hang around. They went in and dropped the food off and left, right? So zero ventilation is just a prescription for bad health and problems and more absenteeism in schools. There are ASHRAE research projects that document all that more ventilation actually is helpful both in absenteeism, but also more helpful in student performance and being able to actually learn and do better on tests.
So Scott, add another comment to that. In the Northeast, there isn't any ventilation other than windows. The heat source is a boiler with radiators. Now, obviously, I don't have any experience with the Northeast systems. Maybe you can speak more to that. Oh
yeah. So there's an interesting article that I've got downloaded someplace. I have way too many interesting articles. So actually the idea back in the 1918 flu pandemic was that this was perfect. We all needed this. We needed this this radiator, the steam radiator, which is what you had. You had this low pressure steam radiator that gave you lots of heat. You opened the window over the radiator, and so you got lots of air coming in and air circulation. And so the prescription for healthy environment was to have an open window and the steam radiator, and that was the thought of how you were going to be healthy and avoid getting the flu and the pandemic, is you're going to have good ventilation and the heat. So the window, okay, I'm going to date myself. Back in college, there was a steam radiator and a window, and that's what I did because there wasn't a very good control on the steam radiator. So I controlled my temperature by the window. I had great ventilation. It was fine. It was dry air, right? But it was still good. It was good. I could sleep well at night. I think that's great, and it was an accepted solution for how to deal with the pandemic of 1918.
Opening windows is not
everything.
something. Opening windows is not something we're used to here in Arizona in the summertime, at least.
No, and sometimes you can't even open the windows. That's the other thing. We've got this design mentality now. We don't want to open windows. We want to control all these things. But we have to kind of get past that. I think the hybrid idea is a great idea of how do you integrate that, the natural ventilation with a forced air ventilation. That is a requirement of 62. If you didn't have an engineered natural system, you need to have a hybrid system, so you can go either or.
Okay. Well, that's all the questions in there. Sorry about my dogs, this
No
working
problem.
from home that we're all used to. But that's all the questions that are in the chat. If anybody else has any questions, you can just jump on real quick or type it in. And if not, I'll give it a couple seconds. All right. Well, Hoy, thank you so much. Dan, I don't know if you have anything.
No, Hoy, thank you very much for this very informative presentation, and want to thank all of those who joined us today, and we appreciate you taking the time. And please let us know at any time your comments, how we can continue to expand upon our educational platform to promote smart, intelligent HVAC design.
Absolutely. And then next month, we are doing humidification as our topic. So you'll see that come out here soon.
All right. Appreciate the opportunity. Thanks, everybody. Have a great St. Patrick's Day.
Thank you, Hoy.
You too.
All the best.
Bye.
Bye-bye.